Welcome to today's Explainer, where we're throwing three major text classification paradigms into the ring to see which one you should actually implement. If you're building AI applications right now, you already know that categorizing text is absolutely foundational. But the way we actually do it, it's completely fractured. Do you just ask a large model for the answer? Do you feed it a few examples? Or do you roll up your sleeves and train a model from scratch? Well, today, we're settling the debate.
So how do you actually choose the right model? With so many options out there, it can feel like a guessing game. But we're going to dive into a recent, incredibly comprehensive benchmark to help you figure out exactly which approach fits your specific problem. We're pulling our insights from a fantastic, fully containerized GitHub benchmarking project. It strips away all the guesswork and gives us hard, cold data so you don't waste weeks building the wrong pipeline.
Here is our roadmap for the Explainer. We'll set up the Showdown, analyze the stats on zero shot, few shot, and our heavyweight fine-tuning, and finish up with a highly practical decision flowchart.
Let's kick things off with Part 1, the Text Classification Showdown. To set the stage, this benchmark leverages the Hugging Face ecosystem and the classic AG News dataset. And it's all running on Docker with NVIDIA GPUs, ensuring these metrics are grounded in a completely realistic deployment environment. What we're really evaluating here is the ultimate modern trade-off, simply prompting a model versus actually getting in there and updating its internal weights. In-context learning, just talking to the model, is super popular right now. But does it really hold its own against traditional full-model fine-tuning?
We'll be judging our contenders across 4 crucial battlegrounds to find that perfect balance. Because, let's be real, it's never just about who gets the highest accuracy score. If your model is flawlessly accurate but takes 3 full seconds to read a single sentence, it's literally useless for a real-time app. We have to weigh accuracy against inference latency, the memory footprint on your GPU, and how much data you actually need to get off the ground.
Let's meet our first contender in Section 2, Zero Shot, the quick starter.
As the name implies, zero shot means zero pre-labeled examples. You just pass in your text, define your categories, and let the model rely totally on its pre-existing knowledge. And hitting a baseline accuracy of 74.5% with absolutely no training data, that is a massive hero stat. Think about that for a second. Without gathering any examples or updating a single weight, you're instantly hitting nearly 75% accuracy. For a rapid prototype, that feels almost like magic.
But hold on, zero training definitely does not mean zero cost. During inference, you're still chewing up 1850.5 megabytes of GPU memory just to process those prompts. You have to load a pretty heavy model into memory to handle those zero-shot requests. So yeah, it's incredibly fast to develop, but it absolutely commands a real footprint on your hardware.
Moving right along to Section 3, Few Shot, the context sketcher.
This is where we step into in-context learning. You give the model a handful of correctly categorized examples right in the prompt to gently steer its behavior. Now, while this definitely gives you better contextual understanding, the benchmark revealed a huge catch. The model becomes incredibly sensitive to the specific examples you choose. Pick a slightly weird example or mess up your prompt format, and your performance swings wildly. You are totally at the mercy of how well those few examples represent your data.
And here is its fatal flaw. Increasing those examples significantly spikes your latency, hitting a massive 1,250.4 milliseconds just for 16 examples. And we're talking about P99 latency here, the worst-case scenario for 99% of requests. Taking over a full second to classify a single piece of text just because you added 16 examples, that's a massive bottleneck for any high-throughput system.
So the true cost of few shot is really twofold. Beyond that latency bottleneck, you have serious instability. That 0.045 standard deviation reveals real variance across runs. When the researchers just swapped out the random seed for 8 examples, meaning they just changed which 8 examples the model saw, the results jumped around. In production, having your app perform differently just based on which handful of examples it randomly pulled, that's a huge headache.
Which brings us to Section 4, Fine-Tuning, the heavyweight.
This is the traditional heavy-duty approach, passing thousands of examples through a model, calculating gradients, and actually updating internal weights so it becomes a specialized expert. And the results? Fine-tuning absolutely crushes prompting methods, boasting a staggering 94.2% accuracy. A nearly 20-point jump over zero shot is just monumental. This is the difference between a prototype that sort of works and a bulletproof enterprise-grade application you can comfortably put in front of millions of users.
And it backs up that accuracy with an incredible macro F1 score of 0.935, completely cementing its status as the performance champion. This score is vital
because it proves the model isn't just cheating and guessing the most common category. It's performing consistently across all the different classes. Fine-tuning genuinely transforms the model into a true domain expert.
Plus, it's blazing fast. When you utilize batch processing, inference latency drops all the way down to just 2.1 milliseconds per example. Compare that to the 1250 milliseconds we saw with few-shot prompting. It's a night and day difference. Even if you're only processing one single item at a time, your median latency is just 15.4 milliseconds. But batch 128 examples together, your throughput becomes wildly efficient.
Yes, the performance is flawless, but you have to acknowledge the heavy upfront costs. We're talking 42.5 minutes of training and over 4,500 megabytes of peak memory just to get started. You can't just fire off an API call and be done with it. You need a dedicated GPU environment, you need to sit around for 40 minutes while it learns, and you need the actual technical infrastructure to manage those weight updates.
All right, Section 5. Which should you choose? Now that we've seen the power levels and the costs, let's build a practical decision tree. The absolute first question you need to ask yourself is, do you have labeled data? It sounds incredibly basic, but it's the defining line in modern machine learning. Are you sitting on a goldmine of historical, categorized text, or are you literally starting from scratch?
If the answer is no, stick with Zero Shot. It's absolutely perfect for rapid prototyping or for highly dynamic label sets, where creating a whole data set just isn't feasible. Like, if your marketing team changes the categories every single week, you simply do not have the time to label new data and run a 40-minute fine-tuning job every time. Zero Shot lets you pivot instantly. But if you do have data, you pass through to the next filter.
Okay, you answered yes. Your next filter is figuring out exactly how much data you're working with. The raw volume of your data totally dictates whether you can safely update model weights or if you need to just rely on in-context prompting. For very little data, meaning anywhere from 10 to 100 examples, Few-Shot is your best bet. It gives you context without overfitting. If you try to fine-tune a model on just 50 examples, it's literally just going to memorize those 50 and fail entirely on new data. But if you have sufficient data, specifically over 500 examples, you're ready for the big leagues.
If you need speed at scale, a batched, fine-tuned model will vastly outperform large language model prompting every time. If you have those 500-plus examples, use them. Take a highly efficient, smaller architecture like DistillBERT, fine-tune it on your data, and process your text in batches. Your cost per token and your latency will be drastically lower than if you were prompting a massive generalized LLM.
I'm going to leave you with this final thought. When you look at your system, what is your true bottleneck? Is it the raw milliseconds it takes to process a document, or is it the human friction of constantly updating shifting categories? You can't perfectly optimize for both, so which one is actually holding your application back?